The first section of our Principles of Flight refresher will be flight dynamics. In this section, we'll look at motion, energy management, and load factor. So, starting from the very first principles of motion. Newton's first law states that a body at rest will tend to stay at rest, and a body in motion will tend to stay in motion in a straight line unless acted on by an external force. So, whilst the forces are in equilibrium, the body will continue to move in a straight line until that external force acts, at which point the deviation will happen in proportion to that force. Why is this important to us? Well, for us in an aeroplane, we try to generate external forces in order to generate a movement with the aircraft. In this case, where we've rolled an aeroplane, we've used the ailerons to convert kinetic energy into a lateral force, which has enabled us to move the aeroplane in the roll dimension. The aeroplane will not move unless we've generated that force. That force comes from the kinetic energy of the aeroplane, the movement of the airflow over the surfaces. So therefore, force requires energy. So let's have a look at the energy and how we manage that. The first kind of energy that we have available to us is chemical energy, the fuel that we're carrying. Burning the fuel releases energy that we can convert into height or airspeed. We are continually expending a certain amount of this chemical energy just to maintain our flight in a straight line unaccelerated, and that's because we're trying to overcome the drag of the aeroplane. We can accelerate using this engine power, burning this chemical engine, and convert into kinetic energy, the energy due to the movement of the aeroplane. This enables us to have aerodynamic forces on the aeroplane, which gives us a maneuver capability. The kinetic energy increases with increasing airspeed. Equally, we can use the chemical energy to climb the aeroplane using engine power, overcoming the force of gravity to give us potential energy. So potential energy is governed by the height above the terrain and increases with increasing altitude. It's potential energy because we have the potential from the altitude to convert into kinetic energy. We can do this through diving the aeroplane, trading our height for speed. Equally, we can use an excess of kinetic energy, excessive speed, to zoom climb and trade speed for height. Throughout this whole system, of course, there is some loss whilst we're trading energy states due to the drag. But overall, this gives us the opportunity to manage our energy throughout the flight regime. The potential energy that we have in the aeroplane, plus the kinetic energy, gives us our energy state. And within this, for any given energy state, we have a zero-sum game. We can trade our kinetic energy into potential energy by zooming, and we can trade our potential energy into kinetic energy by diving. But the net result will be a trade-off between these two types of energy. Only kinetic energy can generate the aerodynamic forces that we require to give us our maneuver capability. But note that the pilot does not control the energy, but rather the orientation and the magnitude of forces on the aeroplane by maneuver. These forces are a result of accelerations on the aircraft, and the result of those accelerations is a change in orientation and direction and magnitude of the flight path vector. Taking this down into the most simple terms, ultimately airspeed and altitude dictate the energy state of our aircraft, and it is that energy state, the combination of altitude and airspeed, which dictates our ability to maneuver. In modern high-performance jet transport aeroplanes, great pains have been taken by the designers to minimize the drag in the cruise configuration. And therefore, large energy trades, trading that speed for height or height for speed, can easily overshoot the desired outcome. And as aeroplanes are heavier, there is a certain amount of anticipation which is required due to the inertia of the aeroplane, the tendency for it to continue in its existing condition. Looking at our three types of energy, the chemical that we can convert into kinetic or potential energy, the kinetic energy which we can convert into potential energy by zooming, or the potential energy which we can convert to kinetic energy by diving. There are certain limits within which we seek to keep. First of all, for potential energy, we have the limits of the terrain below us, and buffet altitude, our limiting altitude above us. For kinetic energy, we have to keep between the aeroplane in a stalled condition and the placard speeds. For chemical energy, we simply have to keep away from empty tanks. So let's move on to a discussion about load factor. But what is load factor? It is a measure of the acceleration being experienced by the aeroplane. Importantly, whilst we often think about load factor in terms of a force which is forcing us into our seat or out of our seat in the vertical plane, load factor can be across any dimension. If we look at Newton's second law, we can see that force equals mass times acceleration. And note that acceleration in this context is not just the aircraft speeding up, it refers to a change in either magnitude or direction of the force. So therefore we may have a speed constant, but we're turning, and in that case the aircraft is accelerating in the direction. For ease, we refer to the force exerted by gravity as g, and the acceleration that we feel is by gravity is equivalent to 9.81 meters per second squared. We use this figure as a benchmark for all other forces acting on the aeroplane and refer to this as g-force. And the load factor that we're feeling in any given direction we consider as a multiple of g, so a multiple of this 9.81 meters per second squared. The load factor can occur in any plane. It can be a longitudinal acceleration, a speeding up and slowing down of the aeroplane. We can have a lateral load factor, an acceleration side to side. Or we can have an acceleration in the normal axis, the up and down, and it's this one which we feel through forcing us into the seat or forcing us up out of the seat. So if we have an aircraft in straight, level, unaccelerated flight, the weight of the aeroplane will pull it down, the lift of the aeroplane will pull it up. The weight will be at 1g, and if we are in straight, level, unaccelerated flight, the lift will also be at 1g. The aeroplane's speed will be constant, and this will balance the drag force felt by the aeroplane. The result of this will be our straight, level, unaccelerated flight. If we have another aeroplane where the speed is constant, it balances the drag perfectly, so we are maintaining a constant airspeed. The weight still acts towards the centre of the Earth at a constant 1g. But now we have a lift which is twice the lift required to balance the weight force. We will now feel an acceleration of 2g. The result of this acceleration will mean that the speed is constant, but we'll have an acceleration in the normal axis. So we will follow an arcing flight path. If we have a vertical flight path, the aeroplane's weight will be acting towards the centre of the Earth. The drag will also be acting towards the centre of the Earth in this case, and the thrust will be less than the total of the weight and the drag. This will have the result that we are following a perfectly vertical flight path, assuming we have no lift being generated by the wings. If we take the same aeroplane and now generate lift on the wings, we'll be in a decelerating flight path, but not straight. And this acceleration in the normal axis will be due to the imbalance of forces. In this case, we have nothing to counter the lift that we are generating, so the aircraft will have a resultant force which will cause us to accelerate in the normal plane. Modern certification standards for aeroplanes in the normal axis give us a load factor envelope of -1g to +2.5g. Handling of the aeroplanes is demonstrated during the test regime as safe up to these limits. So within these boundaries, within a safe speed range, Pilots can manoeuvre without exceptional strength or skill. In the next briefing, we'll move on to have a look at the forces in flight which generate this load factor.